Imagine you are sitting at your terminal right now. Type a single line of text, you hit enter, and you just wait.
Yeah, and exactly 21 seconds later, you have a complete enterprise-grade, globally distributed SAP infrastructure spun up.
Right, it's wild. We were talking about fully isolated subaccounts, hyper-specific regional routing, cost centers automatically attached, all entitlements fully provisioned.
I mean, 10 years ago, orchestrating that exact level of infrastructure took, what, 6 months of committee meetings, procurement delays?
Oh, at least. And an absolute army of systems administrators clicking through graphical user interfaces.
Exactly. And today, it takes a single configuration file. But, there's a massive catch to that power.
A terrifying catch, honestly. Because if you handle that one configuration file incorrectly, if you misunderstand the underlying mechanisms of how that code translates into reality, you might just expose your entire corporate network to the public internet.
Or worse, yeah, permanently corrupt the state of your production environment. The stakes are just incredibly high because we're bypassing all those traditional guardrails.
Right, the guardrails you get with manual configuration, what we usually call ClickOps in the SAP BTP cockpit.
Yeah, exactly, ClickUps. Because in the graphical user interface, it prevents you from doing certain destructive things, right? It grays out buttons, it forces these annoying confirmation dialogues.
But when we move to infrastructure as code, or IAC, you are wielding the raw, unadulterated power of the underlying REST APIs.
Which means the code does exactly what you tell it to do, at terrifying speed with absolutely zero hesitation.
I mean, if you tell it to delete a critical production sub-account because of, I don't know, a misplaced bracket in your code, it will execute that demolition in seconds.
It absolutely will. Which brings us to the exact mission of this deep dive today.
Right. We are moving entirely away from the BTP cockpit UI. If you are a technical practitioner, an architect, or a platform engineer staring at a blank Visual Studio Code development container, right now your instinct might be to jump straight into the web browser to see your SAP landscape.
Resist that urge. Seriously, don't do it. We're staying in the terminal today.
Yes, we are going to build a foundational, secure, and highly scalable setup for the SAP Business Technology Platform, entirely using Terraform.
We're going to unpack the HashiCorp configuration language, the strict structural dependencies, the exact CLI commands, and the terrifying reality of state file management.
No fluff, no high-level executive summaries. We're going for maximum technical density here.
So if you are following along in your sandbox environment, you need your prerequisites met. You have a BTP trial or an enterprise global account, your machine is running Docker or a dev container, and you are ready to author your very first HCL scripts.
But before we write a single line of code, we really have to understand the fundamental physics of the tools we are using, because we have two completely different universes colliding here.
Right, the Terraform engine on one side and the SAP BTP environment on the other.
Let's dissect that collision, because I see so many engineers make a critical conceptual error right out of the gate. They assume Terraform is an SAP fault.
Oh, yeah, it is absolutely not.
Not at all. The core Terraform engine, which is compiled in the Go programming language, is a generic cloud-agnostic binary.
Right. Out of the box, Terraform does not know what SAP BTP even is. It has zero concept of a BTP subaccount, a Cloud Foundry space, or a global directory.
Honestly, it doesn't even know what an AWS EC2 instance is. The core Terraform engine is essentially just a highly advanced text parser and a state calculator.
That's a great way to put it. It reads your configuration files, figures out a dependency graph, and that is it. It has no native ability to speak to any cloud provider's REST API.
So what is the mechanism that bridges that gap?
Well, that would be HashiCorp's modular plugin architecture. We call these plugins providers.
Okay, so you can think of the Terraform provider as like a highly specialized universal travel adapter.
Exactly. The core Terraform engine is the plug. It has a standard shape, a standard way of outputting energy, which in this case is the declarative HCL framework.
Right, but the wall outlet, SAP BTP, requires a very specific voltage, a very specific pin layout, and a highly specific communication protocol.
And the BTP provider sits right in the middle. It translates the generic commands from Terraform core into the highly specific imperative REST API calls that SAP BTP requires to actually build the infrastructure.
I want to push on that translation mechanism for a second. When you say it translates declarative code to imperative API calls, what is mechanically happening under the hood there?
Sure. Yeah.
Like if I write a line of code saying I want a sub-account, How does the provider physically execute that? Is it just, wrapping standard command line curl requests?
No, it is far more sophisticated than just a simple curl wrapper. When you declare that you want a subaccount in your code, you are defining a desired state.
Right.
And the SAP BTP provider, which by the way is actively maintained by SAP and written in Go, receives that desired state via a local gRPC connection from the Terraform core engine.
So it's using gRPC locally to talk between the core binary and the provider plugin.
Exactly. The provider contains the hard-coded logic of the SAP BTP control plane APIs. It knows that to create a subaccount, it must construct an HTTP POST request. It has to format your desired parameters into a highly specific JSON payload, attach the correct authentication bearer tokens, and send it to the exact BTP endpoint URL.
And if you change a parameter later on in your code,
Then the provider knows it must send an HTTP PUT or PAT-CH request to update it. If you remove the code entirely, it sends an HTTP delete request. The provider abstracts all that brutal complexity of REST API lifecycle management completely away from you.
that makes the provider the most critical dependency in this entire architecture. So in our blank VS Code environment, the very first thing we must do is instantiate that working directory and tell Terraform to go fetch this specific travel adapter.
Exactly. So in your terminal, initialize your project space. Create a directory, maybe call it Learning Terraform SAP BTP, and navigate into it.
And the foundation of any Terraform project is the provider configuration, right?
Yes, you create a specific file named provider.tf. This is where we declare all our dependencies.
You need to direct Terraform to the public HashiCorp Terraform registry, which is the centralized repository for all these plugins.
Right, so inside provider.tf, you author a Terraform block, and nested inside that, you author a required providers block.
And the syntax here is incredibly strict because Terraform uses this to query the registry's API. You specify a local name for the provider, usually just BTP, and then you provide a source map.
Yeah, the exact string to declare for the source is SAP/BTP, all inside quotes.
And you must pin the version. You include a version parameter, perhaps tilde greater than 1.0.0.
That is so crucial. Version pinning ensures absolute reproducibility.
Right, because if SAP updates the provider tomorrow and introduces a breaking change to their API payload structure, your deployment will fail if you blindly pull the latest version.
Exactly. Pinning guarantees the execution remains identical every single time your pipeline runs.
So we have instructed the core engine to download the BTP translation layer. But downloading the plugin isn't enough, is it? We have to configure it.
No, you have to point it at your specific slice of the SAP landscape. So underneath that Terraform block, you create a provider BTP block. This is where we pass arguments directly to the plugin itself.
And the most critical mandatory parameter here is the global account string. Let's talk about why that parameter is absolutely mandatory.
Well, SAP BTP uses a strict hierarchical structure. At the very top is your global account. This is the root tenant, the billing entity, the absolute top-level domain of your entire SAP landscape.
Everything, provision directories, subaccounts, Cloud Foundry spaces, HE and databases, it all exists underneath this global account.
Right. So the Terraform provider needs to know the exact endpoint route to target its subsequent API calls.
If you log into your BTP cockpit right now, click on your global account and look at the URL or the overview page, you will find your subdomain string.
Yeah, if you are in a trial environment, it usually looks like an alphanumeric string starting with something like EF and ending in trial-ga.
You take that exact string and map it to the global account parameter in your provider.tf file.
And just like that, the provider now knows what to talk to and where to direct the HTTP requests. But we have arrived at the most critical security juncture of this entire architecture.
Authentication. Because the BTP API control plane is not going to just accept anonymous POST requests to spin up costly infrastructure.
Definitely not. It needs to know who is asking, and it requires cryptographic proof.
And here is where I see the most dangerous, terrifying anti-patterns in cloud engineering.
Oh, I know exactly what you're going to say.
The SAP BTP provider supports a username and password authentication flow. If you look at the provider documentation, you will see optional parameters for username and password inside that provider block.
And the temptation for a junior engineer is to just type their SAP ID and password directly into the provider.tf file in plain text.
Just so they can get on with their day and test their code. But as an enterprise architect, if I see that in code review, that is an immediate hard stop.
It is a catastrophic vulnerability. The moment you type a plain text password into an HDL file, you run the massive risk of committing it to version control.
Right. If you push that to a GitHub repository, even a private one, you have compromised your entire global account.
Automated scraping bots look for leaked credentials on GitHub 24/7. They will find that password in seconds.
And malicious actors will use it to spin up massive HANA database instances in your account for crypto mining. You'll rack up tens of thousands of dollars in consumption costs before you even wake up.
So we absolutely must isolate the credentials from the code. The infrastructure code should be entirely agnostic of the identity that's running it.
Instead of hard coding, we use dynamic runtime injection. The SAP BTP provider is explicitly programmed to look for two specific environment variables on your host machine if the credentials are not found in the HCL block.
Right, it looks for BTP username and BTP password.
But our baseline scenario is a VS Code development container. We are not running this natively on a MacBook or a Windows machine. We are inside an isolated, ephemeral Docker container.
So the standard methods of authentication injection, like, typing an export BTP use surname equals guys-iz command into your terminal, or maintaining a local .bashak profile, those just do not apply here.
Right, the moment you rebuild or restart that container, those terminal exports are wiped from memory.
Which introduces an interesting architectural challenge. How do we persistently, yet securely, inject these variables into an ephemeral container runtime?
Without baking them into the Docker image itself, which would obviously be just as bad as putting them in the HCL.
Right, the exact mechanism in a dev container architecture relies on a specialized configuration file. In the root of your project directory, alongside your .devcontainer.json configuration, you create a file explicitly named devcontainer.nv.
Okay, so a dedicated environment variable file that the VS Code container engine looks for during the bootstrap phase.
Exactly. And the syntax inside this file is remarkably simple but highly specific. You do not use the export command here.
You simply declare key value pairs. So BTP username equals your mail at domain.com on line 1, and BTP password equals your super secret password on line 2.
Right, no quotes, no spaces around the equal sign, just raw key value pairs.
And what happens when you command VS Code to rebuild and reopen in container?
The Docker daemon actually reads that devcontainer.n file. It takes those raw key value pairs and injects them directly into the runtime memory of the container's operating system environment.
So when your terminal finally loads, those variables are already securely sitting in memory.
Exactly. Furthermore, VS Code automatically grays out this file in the Explorer, usually tying it to a .gitignore template, ensuring that this local .n file never touches your Git repository.
The structural isolation is absolute. The code is public, the execution environment is private, and the bridge between them is memory-injected authentication.
That is the foundation right there. We have a secure, authenticated translation layer capable of translating generic code into SAP BTP API calls. We are finally ready to author the actual infrastructure.
We need to build something physical, or, well, logically physical in the cloud.
The standard starting point for any SAP architecture is the subaccount. So, in your working directory, instantiate a new file named main.tf.
Now, why main.tf? I mean, Terraform parses every single file in the directory that ends in .tf, regardless of what it's called.
That's true.
I could name it infrastructure.tf or subaccounts.tf, and a Go binary would compile it exactly the same. So why do we strictly enforce main.tf?
It is entirely about human readability and enterprise standardization. When a site reliability engineer is paged at 3 a.m. because a deployment failed, they shouldn't have to hunt through a dozen arbitrarily named files to find the entry point.
That makes sense.
Main.tf is the universally accepted canonical root of your primary domain configuration. It signals to any engineer reading the repository, start here. This is the core logic.
Okay, so inside that main.tf, we declare a resource block. This is the core primitive of the HashiCorp configuration language.
You type the keyword resource, followed by a string representing the exact resource type from the provider, which is BTP subaccount.
Then you provide a second string, which is the local Terraform address. Let's name it project subaccount.
That second string, that local address, requires some clarification. When you name it project subaccount, that string never leaves your laptop.
Right, it's not sent to the BTP API.
Exactly. It is strictly an internal identifier for Terraform's own dependency graph. If you need to attach an entitlement to this subaccount later in your code, you will reference bttp subaccount.projectsubaccount.ii. It basically creates a locally addressable object in memory.
The actual data that gets sent to SAP exists inside the curly braces of that resource block. We have mandatory parameters that the API absolutely requires to formulate a valid HTTP POST request.
You must define a name. This is the display name that humans will actually see when they log into the BTP cockpit.
You also must define a subdomain, which acts as the unique URL route for this specific subaccount.
And critically, you must define a region. The region parameter is where the theoretical cloud meets hard physical data centers.
Right, because SAP BTP doesn't exist in a vacuum. It sits on top of hyperscale infrastructure providers like AWS, Azure, Google Cloud, and Alibaba.
And if you are operating in a trial landscape, your physical region options are strictly limited by SAP to control costs.
You are generally restricted to US 10, which corresponds to an AWS data center in US East, usually Virginia, or A21, which is AWS in Singapore.
Yeah, so we will hard code US 10 for this deployment scenario.
But let's elevate this from a sandbox exercise to a rigorous enterprise scenario. You are never just spinning up isolated subaccounts for fun in a production environment.
Never. That subaccount belongs to a business unit, a specific project, and most importantly, a specific budget.
In enterprise architecture, if you do not attach metadata to a resource at the exact moment of its creation, it becomes a rogue, untrackable asset in your billing dashboard.
Yeah, the platform administrators and FinOps analysts will have absolutely no idea who owns that $5,000 monthly consumption bill.
To solve this, the SAP BTP API supports resource tagging, which in Terraform is exposed via the labels parameter inside the resource block.
But here's where we hit a fascinating nuance of the HashiCorp configuration language. You cannot just pass a simple string or a basic JSON object to the labels parameter.
Right, because HCL is strictly typed and built on Go. And because the SAP API expects a very specific data structure for metadata, the provider documentation mandates that the labels parameter takes a map of sets of strings.
A map of sets of strings. We really need to unpack the logic behind that complex data structure. Why is it so layered?
Well, a map in HCL is a collection of key-value pairs, similar to a dictionary in Python. The keys are the label categories, for example, stage or cost center.
But the SAP API allows a single category to hold multiple values, right?
Exactly. A subaccount might belong to both cost center A and cost center V. Therefore, the value assigned to the key cannot be a single string. It must be a set of strings.
And a set is an unordered collection of unique values. So in your HCL execution, you open a labels block. Inside, you define your map key, so stage equals. Then you define your set using bracket syntax, so bracket, quote, dev, quote, bracket.
On the next line, you define another key, so cost center equals bracket, quote, CC7892, quote, bracket.
You are explicitly formatting complex, multidimensional metadata perfectly structured for the BTP control plane to ingest.
And while we are defining optional parameters, we should also pass the Boolean argument, bit equals true.
Oh yeah, that's important for sandboxes. It flips a bit on the ATI payload that allows this subaccount to access early release BTP services.
Right, which is essential for a testing environment. So the code is authored, the main.tf is syntactically complete, the provider.tf is pointing to the right global account. The credentials are injected into memory.
Now we transition from authoring to orchestration. We move into the CLI workflow.
This is where we execute the Terraform lifecycle commands. We have to deeply understand what the Go binary is doing at each step.
Step 1 in any new Terraform workspace is Terraform init. From an architectural perspective, this is the bootstrap phase.
When you execute this, Terraform scans your working directory, reads the .tf files, identifies the SAP/BTP provider requirement, and reaches out to the HashiCorp registry over the internet.
If you are watching your file explorer in VS Code when you hit enter on init, you will witness the mechanics in real time. A hidden directory named .terraform is dynamically created.
And inside this directory, Terraform downloads the actual compiled Go binary for the SAP BTP provider for your specific operating system and architecture.
Like Linux AMD 64 for a standard dev container, but it doesn't just download the binary, it also generates a file in your root directory called terraform.lock.hcl.
That is a crucial security mechanism right there. The lock file calculates and stores the cryptographic SHA-256 checksums of the provider binary you just downloaded.
This completely prevents supply chain attacks.
Right. Because if a malicious actor compromised the HashiCorp registry tomorrow and replaced the SAP BTP provider with a corrupted version that steals credentials,
And you ran Terraform init on your machine.
Terraform would calculate the checksum of the new binary, see that it doesn't match the cryptographic signature locked in your terraform.lock.hcl HCL file and immediately abort the execution with a fatal error.
It absolutely guarantees the integrity of your translation layer. It's brilliant.
So once initialized, the very next command you must type is Terraform FMT. That stands for format.
In a collaborative engineering environment, stylistic arguments over code indentation or the alignment of equal signs are a massive waste of time.
Oh, completely. Terraform FMT leverages an abstract syntax tree parser to read your HCL, completely ignore your personal formatting choices, and rewrite the file to conform to canonical HashiCorp formatting standards.
It standardizes the indentation to 2 spaces and aligns all your assignment operators. You run this to ensure your Git diffs show actual code changes, not just white space manipulation.
All right, the code is downloaded, locked, and formatted. Next command, Terraform validate. Now let me challenge this standard workflow.
Okay, go for it.
If we are about to run a planning phase that calculates what we are going to build anyway, why do we need a separate validation step?
Yeah.
Doesn't the plan command inherently catch broken code?
It does, but it does so incredibly inefficiently. Terraform Validate is designed for instant feedback. It performs strict static offline analysis.
Meaning it doesn't touch the network.
Exactly. It does not look at your BTP credentials. It does not attempt to resolve DNS or establish a TLS handshake with the SAP BTP API. It strictly analyzes the local abstract syntax tree of your configuration files.
Did you forget a closing brace? Did you attempt to pass a Boolean into a parameter that expects a map of sets of strings? Did you reference a variable that doesn't exist?
Right. Validate catches those syntactical errors in milliseconds.
It's all about network latency and failing fast. If you skip validate and jump straight to plan, Terraform initiates the full API handshake.
Which can be slow. You might wait 30 seconds for authentication, routing, and state locking over a slow enterprise VPN, only to get an error saying you misspelled the word resource.
Exactly. You use validate to guarantee the code is structurally sound before you spend time sending packets over the wire.
Assuming validate returns a success message, we execute the most complex analytical command in the toolchain. Terraform plan out, TF plan.
The planning phase. This is the absolute core genius of Terraform. When you run plan, the core engine constructs a directed acyclic graph, or a DAG.
It maps out every single resource you ask for and every single dependency between them.
It then authenticates against the SAP BTP API using your injected environment variables, and it queries the global account to ask what currently exists in reality.
Right. It performs a massive delta calculation. It compares your main.tf, your desired state, against the API response, which is the current state.
And in our blank sandbox, the current state is obviously empty.
So Terraform calculates the diff and outputs an execution plan to your terminal. It will literally say, I need to perform one creation action, BTP subaccount.project subaccount.
Notice the specific flag we use there, -out TF plan. We are not just printing the plan to the screen.
No, we're instructing Terraform to serialize that exact cryptographic execution blueprint into a binary file named TF plan. We are freezing the delta calculation in time.
But when you review the terminal output of that plan, you will see all the parameters we hard-coded. You'll see region equals US10, Batenable equals true.
But you will also see several crucial fields, such as id, parented, or state, listed with a very specific phrase, known after apply in parentheses.
That phrase is Terraform admitting a fundamental truth of cloud architecture. It does not control the database.
Right. Terraform can ask SAP BTP to create a subaccount, but Terraform cannot predict what the universally unique identifier, the UUID, of that subaccount will be.
The SAP BTP underlying database generates that UUID at the exact millisecond of creation. Terraform acknowledges this dependency by marking it known after apply. It knows it needs that ID later, but it has to wait for the API to hand it back.
Which brings us to the moment of truth, execution. In your terminal, you type Terraform apply TF plan.
Because we are passing the explicit binary plan file we saved a moment ago, Terraform does not pause to ask you to type yes to confirm.
It assumes you already reviewed the blueprint. It immediately initiates the HTTP POS2 requests.
Now, if you encounter an immediate red error stating client could not be created, you do not have a Terraform syntax problem.
No, you have an authentication injection problem. It means your devcontainer.n file was not read by the Docker daemon, or maybe the variable names were misspelled, and the provider attempted to authenticate with null credentials.
But if your environment variables are correctly injected, the terminal output shifts. You will see BTP subaccount.project subaccount : creating.
And then you just wait. The provider is holding the HTTP connection open, polling the BTP API, waiting for the asynchronous creation job on the SAP side to actually complete.
In a standard trial environment, this takes an astonishingly short amount of time. Usually, within exactly 21 seconds, the terminal prints. Apply complete. Resources. 1 added, 0 changed, 0 destroyed.
You have successfully provisioned enterprise-grade SAP infrastructure from a text file. It's incredible.
21 seconds.
Yeah.
It is an absolute paradigm shift in how we manage SAP landscapes. But we have to address the terrifying inverse of that power. We have to talk about Terraform Destroy.
The ultimate undo button.
But it is not a blind undo button. It is a highly calculated, mathematically precise demolition.
Right. If you run Terraform Destroy, Terraform consults its directed acyclic graph again, but it traverses the graph entirely backwards.
This is critical for complex environments. Imagine a scenario where you have a subaccount, and inside that subaccount you have provisioned 5 specific service entitlements and a Kajnan cloud database instance.
If you just sent a blunt API command to delete the subaccount, the BTP control plane might reject it. It would say you cannot delete an account containing active service instances.
Or worse, it force deletes the account and leaves orphaned billing artifacts in the backend that you can't even see anymore.
Terraform prevents that completely because it understands the dependency graph. When you run destroy, it knows it must first issue HTTP delete commands to the database instance.
It waits for the database to physically spin down.
Yeah.
Then it sequentially deprovisions the 5 entitlements.
Then it strips the metadata labels, and only when the subaccount is completely empty does it issue the final delete command for the subaccount itself.
It is ruthlessly efficient, and it will dismantle months of architectural work in about 3 minutes.
Yeah.
You must use it with extreme caution.
But that precise demolition mechanism raises a really profound technical question. After a successful apply, you close your laptop. You come back a week later. How does Terraform remember what it built? When you run destroy, or even just a new plan, how does the engine know the exact UIDs of the entitlements and databases it needs to dismantle? Terraform doesn't just search the entire SAP cloud hoping to find a subaccount that matches your name.
No, it uses a highly specific localized memory bank. And that brings us to the most dangerous, most critical file on your entire hard drive. We have to unpack the absolute source of truth in this architecture: state management.
When you ran that successful Terraform apply and the terminal printed its success message, the core engine performed one final silent operation before returning control of the terminal to you.
It generated a file in your project directory named terraform.tfstate.
Architecturally, the anatomy of this tfstate file is the linchpin of infrastructure as code.
Wow.
Let's explain the exact mechanism of what this file is and what it is doing.
At its core, the tfstate file is just a massive, complex JSON database. It is the physical mapping between your theoretical HCL configuration blocks and the actual, tangible SAP BTP resources living in the cloud.
Remember during the plan phase when we saw those parameters listed as known after apply?
Yes, the UUIDs that Terraform was waiting for the SAP database to generate.
Exactly. When the SAP API completed the creation and returned a successful HTTP 200 OK response, the payload of that response contained all those generated UUIDs.
The internal tracking IDs, the exact timestamp of creation, the resolved region mappings, all of it.
Terraform takes that entire JSON response payload and writes it directly into the terraform.tfstate file. This file is how Terraform tracks the relational dependencies.
It knows that subaccount A has UUID 12345. If you write new code tomorrow to add an entitlement to subaccount A, Terraform reads the state file, grabs UID 12345, and inserts it into the new API request.
Which makes the state file incredibly powerful, but it also creates a massive glaring security vulnerability.
As an architect, the default behavior of the state file absolutely terrifies me.
If you are following along in your sandbox, you have an immediate non-negotiable security requirement. If you are initializing a local Git repository in this directory, the very first thing you must do before you stage a single file for your first commit is open your .gitignore file and add 2 distinct lines.
Terraform.tfstate and terraform.tfstate.backup. We have to be explicitly clear about why this is non-negotiable.
The state file is written in plain, human-readable JSON. There is 0 native encryption on this file on your local disk.
Not at all. It stores every single piece of data returned by the API in absolute clear text. Think about the devastating implications of that in a mature environment.
Right now, we only have a subaccount, but next week you might use Terraform to provision a secure SAP HANA database, or generate internal network IP addresses, or create service bindings with auto-generated client secrets and root passwords.
All of those dynamically generated, highly sensitive passwords are sent back by the BTP API and written directly into Terraform.tf state as plaintext strings. Literally, password colon, quote, super secret 123, quote, right there in the JSON.
If you accidentally commit that state file to your GitHub repository, you haven't just leaked your configuration. You have leaked the administrative root passwords to your entire production database tier.
You have fundamentally breached your own network. You must treat the state file as the most toxic, sensitive, radioactive material in your entire codebase.
And alongside the security risk, there is a massive operational risk. Because it's just a standard JSON file sitting in your directory, the temptation is immense.
Oh, I've seen it happen. You might look at the BTP cockpit and realize you want to change the display name of your subaccount.
So you open terraform.tf state in your VS Code editor. You find the name JSON key, you manually change the value, hit save, and assume you've updated your infrastructure.
That is an architectural death sentence for your workspace.
Man.
I issue a strict warning to all engineers. Never, under any circumstances, manually edit the state file directly.
If you manually alter that JSON, you instantly break the cryptographic continuity of the directed acyclic graph.
Terraform uses complex internal serial numbers and dependency mappings to ensure the state perfectly mirrors reality.
If you change a value, the next time you run Terraform plan, the engine will attempt to reconcile your manual JSON edit with the real-world SAP API response, and it will catastrophically fail.
It will completely lose its mind. It'll throw state corruption errors, and you will permanently break your ability to manage that infrastructure via code.
The only way to fix it is a painful manual state manipulation process using the CLI that takes hours to untangle.
So, if the file is a plaintext security hazard that we are strictly forbidden from opening in a text editor, how are we supposed to interrogate it?
Right.
How do I, as an administrator, find out what is actually running in my environment without going to the BTP web UI?
Well, HashiCorp built native, safe, read-only mechanisms into the CLI specifically for this purpose. You never open the JSON directly, you use the Terraform state command suite.
Let's walk through those commands. If I want to see everything, I run Terraform show.
Yeah. Right. If you run Terraform show, the Terraform binary safely parses the state file in memory. It strips away all the complex internal JSON metadata routing, the serial numbers, and the lineage identifiers.
And it prints the actual resource data to your terminal in a clean, human-readable, HCL-like format.
But that command scales terribly. Terraform show is fine when we have one subaccount, but in a real enterprise environment with 400 resources.
Running Terraform show is going to flood your terminal buffer with tens of thousands of lines of output. It's totally unreadable.
That is why the most common command you will actually use is Terraform state list.
Okay, list.
This command does not print the details. It outputs a highly condensed flat inventory of all the resource addresses currently tracked in the state file.
So in our sandbox, it will return a single line. BTT subaccount.project subaccount.
When you are auditing an environment, stateless is your absolute best friend to quickly see exactly how many databases, directories, and role collections exist.
And once you find the specific resource address you're looking for in that list, you can drill down safely.
Precisely. You use the command terraform state show followed by the exact address. For example, terraform state show btp subaccount.project subaccount.
This command isolates that single object in the dependency graph and prints its exact current configuration details to the terminal.
And this is where the theoretical loop of our deep dive completely closes. If you run that command right now and look at the terminal output, you will see the parented field.
During the plan phase, that field was a theoretical known after apply.
Now it is a fully populated physical UUID string linking your subaccount to your global directory. The state file has successfully anchored the HCL theory into the concrete reality of SAP BTP.
It is incredibly satisfying to see that alignment in the terminal. But as we transition from a single developer sandbox to a massive organizational deployment, we have to address the elephant in the room. We have a severe scaling problem.
An existential scaling problem, honestly. The entire architecture we just built, while structurally sound in theory, is completely unviable for a real enterprise.
Why? Because the terraform.tf state file is sitting locally on your specific hard drive inside your specific dev container.
It creates an immediate catastrophic bottleneck. If you hold the local state file on your laptop, you are literally the only person in the entire corporation who can manage that SAP BTP landscape.
Let's play out a scenario. I am your lead architect. You provision the subaccount on Monday. On Tuesday, you are out sick.
Oh, yeah.
The business needs a critical SAP HNOW database provisioned in that exact subaccount immediately. I pull down the main.tf code from our GitHub repository, I add the database resource block, and I run Terraform plan on my laptop. What happens?
Well, your local Terraform engine creates a brand new empty state file on your machine. It looks at the BTP API and says, I don't track a subaccount here.
As it doesn't have your state file.
Right. So your plan will attempt to create a completely duplicate subaccount, which will fail immediately because the subdomain name is already taken in the real world. You are completely paralyzed.
The local state file is a single point of failure. To enable true collaborative infrastructure automation, the memory of the system cannot live on an engineer's laptop.
It must be stored centrally, accessible to any authorized machine or CI/CD pipeline.
In the Terraform ecosystem, this architectural shift is called utilizing a remote state, and it requires configuring a backend.
A remote backend physically shifts the storage location of that JSON state file off your hard drive and into a centralized cloud storage system.
The industry standards for professional, enterprise-grade setups are highly durable object storage services, AWS S3 buckets, Azure Blob Storage, or HashiCorp's own managed cloud platform known as HCP.
But it isn't just about dumping a JSON file onto a shared network drive. Remote backends solve the single most dangerous problem in distributed computing and collaborative infrastructure: concurrent execution. We really have to explain the mechanism of state locking.
Imagine the exact same scenario, but we are both online.
Yeah.
You and I are both authorized administrators. We both pull down the code. We both make different modifications.
I add a database, you add a message queue.
And by sheer coincidence, we both type Terraform apply in our respective terminals at the exact same millisecond.
If the backend was just a dumb storage drive, both of our local Terraform binaries would read the shared state file simultaneously. They would both formulate conflicting execution plans, and they would both begin hammering the SAP BTP API with HTTP POST requests.
You would immediately trigger a split-brain scenario.
Right.
The BTP API might accept both requests, but the two Terraform engines would try to write their differing realities back to the single state file at the same time,
Permanently corrupting the JSON.
This is where the engineering brilliance of the remote backend comes in. Backends like AWS S3 do not operate alone. They're paired with a highly consistent database layer in AWS. This is typically a DynamoDB table.
And this table acts as a distributed lock mechanism. When admin A hits enter on Terraform plan or Terraform apply, their Terraform binary immediately sends a lock request to the remote backend.
The DynamoDB table registers that admin A's machine currently owns the lock on the state file.
And if admin B, sitting in a different country, tries to run any command that requires reading or modifying the state while that lock is active,
Their local Terraform binary will reach out to the backend, see the lock in the database, and immediately reject the command.
admin B's terminal will explicitly throw an error saying, "Error acquiring the state lock. State is currently locked by admin A."
It forces absolute sequential execution. The system guarantees that only one Terraform process, anywhere in the world, can modify the dependency graph at any given time.
Transitioning your local sandbox to this enterprise model requires writing an explicit backend block configuration inside your provider.tf, entirely shifting where the source of truth lives and how it is secured.
So let's step back and survey the immense ground we've covered today. We started with a completely empty dev container and a daunting architectural challenge, replacing manual SAP BTP ClickOps with automated repeatable infrastructure as code.
We established the core physics of Terraform, a generic Go binary that relies on the SAP BTP Provider plugin acting as our universal translation layer, converting declarative HCL into imperative REST API commands.
We securely managed our authentication, flat out refusing to hardcode plain text credentials. Instead, we leveraged devcontainer.env to dynamically inject our BTP usernames and passwords directly into the container's runtime memory, perfectly isolating our security posture from our source code.
We authored robust HCL, utilizing complex maps of sets of strings to attach vital FinOps metadata and cost centers to our subaccount, hard-coding our regional deployment to use 10.
We executed a flawless, deeply understood CLI orchestration lifecycle. We initialized a cryptographic lock file, formatted our syntax, validated our code offline to avoid network latency, calculated the DAG delta during the plan phase, and executed the API handshake to provision global infrastructure in 21 seconds.
And finally, we confronted the terrifying reality of the .tf state file learning how to safely interrogate the plaintext JSON mapping using native CLI commands, and mapped the architectural necessity of scaling to a remote backend with DynamoDB state locking to prevent catastrophic split-brain corruption.
We didn't just walk through documentation today. We decoded the actual mechanisms that power modern SAP infrastructure deployment. But, I want to leave you with one final, deeply complex architectural puzzle.
A scenario to really test your understanding of everything we've discussed.
We established definitively that the Terraform engine fundamentally writes its state file in plain, unencrypted text. This means that even if you evolve to a professional enterprise setup and you use a secure remote backend, let's say a highly secured server-side encrypted AWS S3 bucket, the core Terraform engine is still writing the raw JSON data into that bucket.
Right, the bucket encrypts it at rest, sure. But anyone on your engineering team who is granted read access to that S3 bucket can simply download the file, open it, and read all the newly generated database passwords, API access keys, and BTP UUIDs in absolute clear text.
Which means your infrastructure repository is still effectively a backdoor to your most sensitive administrative credentials. A security auditor would have an absolute field day with that architecture.
Exactly. You haven't really solved the secret leakage problem. You've just moved it from your laptop to an S3 bucket.
So as an enterprise architect, how do you solve this? How must you evolve your provisioning pipeline to dynamically handle and rotate secrets natively on the platform side?
How do you architect a system using advanced tools like HashiCorp Vault or AWS Secrets Manager combined with Terraform's dynamic data block lookups?
So that a highly sensitive root password is dynamically generated by the platform, injected directly into the application runtime, and never ever passes through Terraform's state file memory in the first place.
That is the absolute bleeding edge of infrastructure security.
That is how true zero-trust infrastructure is built. Explore the mechanics of dynamic data blocks in your sandbox. Challenge your assumptions. And until next time, keep building.